In a stocking, we have single touch, then we have double touch. So these are the two methods. Now, what is a single touch and a double touch method? I have these drawings over here, which we can see to find out the method. So I'm showing you the first of all, the single touch method. In this single touch method, now let's say that we have this magnet over here. This is a magnetic material which is initially unmagnetized. Magnetic material. So this magnetic material is initially unmagnetized, and what I'm going to do, I'm going to take a magnet and I'm going to stroke this magnet in one cycle as I'm showing you over here. So that means that the number of time I'm going to stroke the magnet, it will cause the magnetization of the unmagnetic material. And what is going to happen over here? This side, where I'm moving north, this side will be magnetized as a south pole, and the other side is magnetized as a north pole. So that means that wherever I'm moving or stroking one of the magnetic poles, it causes other magnet to get magnetized. It causes another magnet to magnetize in a way that I'm showing you. So that means that if north is stroked to the left side, the way you are looking at the screen, this side will become south and the other side is magnetized as north. Okay? So in this way, this is called a single touch stroking method. Single touch stroking method. Now we have the other one as well. Now I'm moving on to a double touch stroking method. So I'm looking at this drawing now, and when we look at this drawing, we have both the methods, and you can see both the method at one way. Now, this initially which are marked over here, it's a single touch method. This is a single touch or single stroking method, whereas this is the double touch or double stroking method. Now in this, we are going to take two magnets with two opposite poles over here, and in this case, one of the pole I'm going to take as a soft, and the other I'm going to take as. Now, the south pole is stroked in one direction, like this, whereas the north pole is stroked in the opposite direction. This will cause the magnetization of one of the pole as north pole, where I'm stroking the south pole, and the other pole over here as a south pole. Now you can see when the south magnetic pole is moved towards this side, the north magnetic pole is moved towards this side. It causes magnetization with the south pole, and the south magnetic pole is moved towards this side. This causes magnetization of this pole. So in this way, we can get a magnet formed over here. So now these are the initial methods by which we can magnetize any unmagnetized magnetic material. So this one is called the single stroke method, and this one is called the double stroke. But these methods are not very good to magnetize any magnetic material because they'll give us weak magnetic material. Now I'm moving on to the good method of magnetization. We have studied one thing, and that is the solenoid. Remember that in the last class, when we did about the solenoid, I've shown you this drawing. So, okay. So now I have this method. This is the solenoid. And we have seen in the solenoid, if I'll place any unmagnetized magnetic material, it will get magnetized. Now, how it's going to get magnetized? Now, let's see that. Now, I'm moving this back. Okay. Now I'm going to place an unmagnetized magnetic material. Let's say that this is a magnetic material which is a soft iron. Now, I'm going to place this in a solenoid to magnetize this material. In the solenoid, we have actually an insulating cylinder which is hollow from inside, and I'm going to place wires on this cylinder as a coil. So this is the coil. I'm placing it. Now, if you look at this coil, I'm also using a variable resistor to control the current. I'll switch over here. And a direct current source. Now, in this case, the current is flowing like this in an upward direction. So everywhere, the current is flowing in this way. That means that from top, the current is flowing into the pen paper. So this is current flowing into the pen paper. Guys, are you there? Can you hear me? Hello? Okay. Now, when the current is flowing like this, now I'm going to make one more thing over here. How to determine the direction of the magnetic field. For that, I'm going to make a hand over here. So now, I'm going to apply right hand grip rule. In the right hand grip rule, now how you're going to do? You're going to curl your fingers right hand fingers into the direction of current. Over here, the fingers are curled like this. So this is thumb, which is pointing towards a non-seeking pole. Whereas when you look at the direction of the fingers, the way they are pointed, in this case, as you can see that from the lower region, current is flowing out of the finger paper, and from the upper region, current is flowing into the finger paper. Now, when we point our fingers like this, on pointing our fingers like this, we can see that in this case, this side of the soft iron becomes a north pole, whereas the other side of the soft iron will become the south pole. So this is called the electrical method of making magnetization. So electrical method of magnetization is using a solenoid and providing the solenoid with direct current. And to determine the direction of the north pole, I have to use right hand grip, where I'm going to curl my fingers in the direction of the current, and the thumb will point in the direction of the magnetic. So in this case, we have determined the direction of the north pole, and we have done the magnetization of the soft iron. Now, as we know that there are two types of materials, if we have soft iron over here, the soft iron becomes temporary, but a very strong electromagnet. The strength of magnetism, depends on number of turns, and magnitude of current moving through the coil of solenoid. Okay. And if we have steel, it becomes a permanent magnet. So in this way, we can magnetize any material. If it's a temporary magnetic material, it will turn into a temporary magnet. Whereas if it's a permanent magnetic material, it will turn into a permanent magnet. One of the magnetization method which makes very strong magnet, it's this method. Now, I would like to ask that if you have any question regarding this part, please do ask me. Hello? Hello?
जी sir.
Ji. I hope that you can hear me, every one of you. Please speak.
Yes, sir.
Okay, that's good. Now I'm going back to this part. Now let's say we have discussed two methods over here of magnetization. Now I'm moving on to one of the third method of magnetization. The third method of magnetization, again, this is not as strong as the first method, but this is called magnetic induction. In this case, we need to have a magnet over here. So I have a magnet. This is the north of the magnet, whereas this is the south. Now, if I'll bring any unmagnetized magnetic material, let's say we have soft iron. I'm using the temporary magnet right now. Now, in case of a temporary magnet, what happens? When the magnetic field of this magnet, it passes through the soft iron nail, it turns the soft iron the magnetic field of the permanent magnet, which I've shown you, when it passes through the soft iron nail, it causes the soft iron nail atomic magnets to align themselves in one direction. So now I'm going to show you the alignment of the atomic magnets. So we have this alignment of the atomic magnets. They align themselves in the direction of. So the number of atomic magnets aligned in one direction depends on the strength of the magnetic field passing through each nail. The last atomic magnet, the last nail, you can see that as it doesn't develop or none of the magnetic field is passing through it, so it couldn't become a magnet and it falls off this. Or there is a chance that its strength is quite weak, and as a result, the attractive forces cannot overcome the weight. So now we have these three methods of magnetization. Now I'm moving on to the methods of demagnetization. So looking at the methods of demagnetization, basically for that, I'm going to shift to a new section of the board. They are in the similar manner as we have three methods of magnetization. I have three methods of demagnetization. Moving on to methods. Of demagnetization. Number one is hammering. This is called the mechanical method of magnetization. Number two is heating plus hammering. And number three is electrical method. And I'll be more interested in the electrical method. Okay, now. Hammering. then you can see, in this case, hammering is a very good method. What it does, let's say that in this, we have a magnet over here. So this is a magnet. This is the north of the magnet. Whereas this is the south of the magnet. Now, when this hammer is hitting on this magnet, it distorts its atomic magnets, which were initially aligned. Now the atomic magnets are being distorted. But this is not a good method of demagnetization. Weak demagnetization. On the other hand, if I start heating it as well, then the magnetization, demagnetization will be more strong. But I would either prefer this method of magnetization or any other method apart from the electrical method. And when we move on to the electrical method of magnetization, that will be the best method. Now moving to the initial method, electrical method of demagnetization. In this case, I'm going to place a magnet in a solenoid, which is supplied with alternating current. Now, it's a solenoid, but this solenoid is not supplied with direct current. Instead, this solenoid is supplied with alternating current. And not only it is supplied with alternating current, the solenoid should be kept in the direction of east-west. So this is north, east, and south, west. So now you can see that the solenoid is aligned with in an east-west direction of Earth, and when we supply alternating current, AC, then it will change its direction. Its direction is varied several times during one complete cycle. As a result, the atomic magnets present in it will deorganize, they are distorted, and now they are no more in the same direction. And the distortion is so random that the magnet will lose its magnetism completely. So at the same time, one more very important factor, that gradually reduce the magnitude of alternating current. Now, why we need to gradually reduce the magnitude of alternating current? Because if the magnitude of alternating current is kept constant, then it won't give us the results of demagnetization as we are expecting to have. So now we have 3 methods of magnetization and 3 methods of demagnetization. If anybody in the paper asks you to write the method of magnetization or demagnetization, you're going to always mention the electrical method. Okay? No other method apart from the electrical method. Okay. Now we are moving on to a very important section, and that is magnetic field patterns. So I'm going to show you the magnetic field patterns. When a current carrying conductor, when current carrying conductor is placed in the magnetic field. So I'm going to show you the magnetic field of the permanent magnets. Now I have one magnet over there. And this is a magnetic north. On the other hand,
सर आवाज में थोड़ा मसला आ रहा है काफी देर से।
बेटे किस तरह का मसला आ रहा है?
सर डबल आ
अब
रही है,
क्लियर?
डिस्टॉर्टेड है।
अब आ रही है क्लियर?
हाँ जी सर, बेहतर है।
Okay. So now I have this north that is over there. And the south is over there. I'm going to place a conductor carrying current like this. So this conductor is carrying current into a kind of port. When I'm going to draw the magnetic field around the current conductor, it's something like this, circular. And the direction of this magnetic field, how we can determine the direction of the magnetic field? Applying right-hand grip rule. In the right-hand grip rule, when we point our thumb in the direction of the current, our fingers will curl in the direction of the magnetic field around the current carrying conductor. So right now I'm pointing my thumb in the direction of the current, and the magnetic field is like this, clockwise. Now, at the same time, if I'm going to draw the magnetic field of this magnet, it's going from north to south. Its direction is like this. Whereas from
करना भी लागू गई
this
फेक
direction
क्लॉकवाइज
is
नहीं
like this.
हो गई
Next, can you hear me? I'm rubbing this and making a 2D drawing so that it becomes more clear to you, and then in the end I'll make the 3D one. So I'm going back to this point. We have a salt over here, and we have a current carrying conductor, carrying current into the plane of board away from us. When I'll draw the magnetic field around this current carrying conductor, it's a circular magnetic field, and the direction of this magnetic field can be determined using right-hand grip rule. You point your thumb in the direction of the current, that is into the plane of board, and your fingers of right hand will curl in the direction of the magnetic field around the current carrying conductor. Now when I'll draw the magnetic field of this magnet, it goes something like this. So you can see that from the top, the magnetic field is in the same direction as the magnetic field of the current carrying conductor. But from the lower region, the magnetic field are opposing each other. So this is the direction of the magnetic field, and this is the direction of the magnetic field. And this region, I'm going to mark this region over here. This is the region where there is going to be a cancellation of the magnetic field. Whereas in this region, there will be no cancellation of the magnetic field because they are in the same direction. So when magnetic field are in the same direction, they are not going to cancel each other. But when they are in the opposite direction, they are going to cancel each other. So we are going to look at this thing, that how they are going to cancel each other. Now this part is no more visible to us because over here there is a cancellation of magnetic field which is taking place. Whereas on the upper region, as there is no cancellation, so there will be no now. If I draw the magnetic field over here, the magnetic field seems to be as if they are going this way, a combined magnetic field, which is having a direction like this. So there is no cancellation in this region, no cancellation in this region, but there is a cancellation in this region. Now, due to this cancellation of the magnetic field, what happens? This conductor will experience force in the direction where there is lesser magnetic field. The reason for this force, magnetic field will repel each other. As over here, due to cancellation, there is a smaller strength of magnetic field, whereas in the upper region, there is a larger strength of magnetic field. As a result, when they undergo the repulsive forces that are sideway repulsive forces, the conductor, which is carrying current away from you or into the plane of paper, it will experience a force, a downward force. So the conductor will experience a downward force due to this cancellation of the magnetic field. Now, on contrary to that, if I have current carrying conductor, which is carrying current in the opposite direction and are placed between the two magnets, the similar two magnets. Now we have again a north over here. and the south over here. But now we have a current carrying conductor which is carrying current towards you. Magnetic field around it. It's going to be like this, circular again. But in this case, applying right-hand grip rule, magnetic field is going to be clockwise or anti-clockwise? Can you guys tell me? The field is going to be clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise. So when we point our thumb towards ourselves, that means away from the board, out of the plane of the board, our right hand fingers will curl in an anti-clockwise direction. So that means that the magnetic field will be anti-clockwise. Now in this case, when I'll draw the magnetic field of this conductor, of the magnets, from the upper region, they are going to cancel the magnetic field of the current carrying conductor, because now from the upper region they are in the opposite direction, whereas from the lower region they are in the same direction, so they cannot cancel. Now in this case, the cancellation is going to happen over here. Cancellation. So cancellation is taking place over here, whereas in this case, this region, and there was a reinforcement because of no cancellation of magnetic field. As a result, there will be no more magnetic field in this part. Now, the magnetic field seems to be like this, a continued pattern over here, and a continued pattern over here. Now, the force experienced by the current carrying conductor with the cancellation of the magnetic field is going to be upward. As I've told you in the very beginning, that the force is always experienced in the direction when there is a cancellation of the magnetic field. Now, what I'm going to do, I'm going to place these two current carrying conductors, which I've shown you, together between the two magnets. We get a knot. And there we have a south. And instead of having just one conductor placed over here, I'm going to place two conductors. One is carrying current into, and the other is carrying current out of the plane. As we studied in the previous part, that when we have two unlike current carrying conductors placed together, they'll have a magnetic field like this. So I'm going to play the magnetic field, and that magnetic field is going to be like that one I used to call the hypnotic eye. Because in this case, the field is going to be clockwise. Whereas in this case, the field is going to be anti-clockwise. But though the field is anti-clockwise, but both the fields are in the same direction from the inner region. So as the fields are in the same direction, So the magnetic field of the two conductors are not going to cancel each other. But when we'll draw the magnetic field of this magnet, from here and from here. You can see that they are in the opposite direction. So over here, we are going to find cancellation. And over here, we are going to find cancellation. So these are the two regions of cancellation. Region where cancellation, because of the opposite direction magnetic field is taking place. And in this case, cancellation due to the opposite direction of magnetic field. Okay, now, what's going to happen over here now? Due to cancellation, there will be no more magnetic field over here. So there will be lesser magnetic field. So lesser magnetic field in this part. In the similar manner, due to cancellation, lesser magnetic field in this part. So we have cancellation and lesser magnetic field in these two parts. As a result, this side appears to be like this, and this side appears to be like this as a combined part. And this side is going to experience an upward force, whereas this side is going to experience a downward force. Now let's go ahead, and I'm going to make these magnets, trying to show you in a 3D pattern. So that's a north and that's a south, and I'm going to show you this part as well. So now, let's make a whole conductor over here. This side is positive and this side is negative. We have just seen that in the previous example, that this is going to experience force downward, whereas this side is going to experience force upward. So that means that if we have a coil like this, where current is carried as the way I'm showing you, because from here, current is flowing into this wire, it goes like this, and this is the very flow of the current. So current is flowing over here like this, from here, and this way, the current is going this way. So that means that we can say that in this case, current is going into the plane of paper or plane of board, and in this case, current is flowing out of the plane of board. And during that, what happens? This side experiences a downward force, and that side experiences an upward force. Now, let's say that if I have an axle over here, and I'm going to place blades over here, how these two blades are being rotated? The direction in which the blades are rotating is like this, because this side is experiencing downward force, and this side is experiencing upward force. As a result, we'll have an anti-clockwise rotation of this coil, which I have placed between two magnets. One magnet is showing you a south pole, and the other magnet is showing you a north pole. So what we are actually discussing is called DC motor. DC motor. So this is the way the DC motor works. I would like to ask you if you guys have any question regarding anything till we have studied now, please do ask me. Anyone having any sort of question? Yes, guys?
No, sir.
No, so it's clear? Okay. Now, I'm going to show you the actual design of the DC motor, that how DC motor works. Now, in this case, we have two magnets over here. One is the magnetic pole north, and the other one is the south. This is the coil that I've shown you initially. So this is the coil. I'm going to mark the part where the coil is running. So this part is the carbon brush. This, sorry, I have marked it wrong. So this part is carbon brush, and this is split ring commutator. Now, this green part is actually soft iron, and there are a few features of the soft iron that we are going to look at. But before that, I would like to show you this whole animation, which will help you understand about how DC motor actually works. Now these are the labelings. We have a power source over here, as I've shown you. In this case, where Now this is the power source. These are the split ring commutators, which are marked over here. This is the carbon brush. One side of the carbon brush is connected to the positive terminal, and the other side of the carbon brush is connected to the negative terminal. This soft iron frame, which is having a copper coil over here. So when we switch on the current in the coil, as the current is flowing into the plane of the paper, on this side of the coil, which I'm marking over here, this side of the coil, current is flowing into the plane of the paper. If I mark this carbon brush as C1 and this carbon brush as C2, so this side is taking current into the plane of paper. From this coil, it goes like this, and from this coil, it comes out of over here. So when we apply Fleming's left-hand rule over here, Fleming's left-hand rule is your thumb will show you the force, your index finger will point towards a magnetic field, and your middle finger will point towards the current. So when we are going to apply Fleming's left-hand rule on this case, you will see that one side of the coil is going to experience a downward force, and the other side of the coil is going to experience an upward force. Now I'm switching on this animation so that you can see with what's happening over here in this case. Well, I'll upload this animation instead of showing you over here. Before moving on to any other thing, I would again like to ask you that do you have any problem or concerns that you would like to ask from me now? Are you guys here? Because I'll be continuing with this DC motor stuff in the next class. Yes, guys?
No question, sir.
No question? Anyone having any other question? Any question, not obviously. Yes.
सर हमने ऑल्टरनेटिव करंट अभी पढ़ना है
जी बेटा वो इलेक्ट्रोमैग्नेटिक इंडक्शन में आता है अभी हम पहले डीसी मोटर को कल कंप्लीट करेंगे then we'll study about the loudspeaker magnetic relay and then we'll move on to electromagnetic induction.
Okay, great.
जी बेटा okay so for today, this is the end of the lesson. We'll be studying in detail DC motor tomorrow, inshallah.